Sunil, you should probably share your slides. Sorry.
Well, actually, it's going to be, I'm going to write. Is that okay?
Oh, sure. But where? Like, where is your board? Oh, on the tablet.
Yeah. Hopefully this is going to work.
Yes, it does. And maybe you can scribble something just to check.
Yeah, sure.
Okay. Okay, so I guess we'll start. So we are very glad to have Sunil Chebolu here from Illinois State in Normal. But of course, I know Sunil because he taught me some mathematics in college. So Sunil is going to talk today about how many units can a commutative ring have. Over to you, Sunil.
Okay, so thank you. So it's a pleasure to speak in this seminar. It's my first time here speaking. I want to thank the organizers for inviting me. So I know Amri and Apurva from way back. So it's good to be here. So I'm in Normal, Illinois, as Apurva said. So I'm here in the Chicago time zone. Time just here is 12 a.m. So my bedtime is at usually at around 10:30, 11. So I'm talking way past my bedtime. If I make mistakes, I have a good excuse today, I guess.
By the time we end, you'll be normal 01.
I guess so. I hope so. All right, so let's begin. So this is some research on a problem in algebra. I know this is a mixed bag, algebra, representations, and combinatorics. There are some connections to these areas, but today mostly we will be on the algebra side. I might allude to some connections in representation theory or combinatorics if I have time. So the main talk is about a problem in algebra first posed by Laszlo Fuchs, who was a American-Hungarian mathematician. But I chose this as the title because it's kind of more intriguing. So I thought it will be drawing people's attention. So let me start off with this simple thing, which was first observed by Galois, approved by Galois, that if you have a finite field, so then the cardinality of F is a prime power. So this is a well-known result, but it was, I think, to the best of my knowledge, first proved by Galois. Okay, so now you can ask the same question for a finite commutative ring. So question, so let R be a finite commutative ring. So the first thing about finite fields is you find that in pretty much in every textbook in abstract algebra, every finite field has cardinality of prime power, and moreover, there is a unique finite field given any prime power with that cardinality. So what about finite commutative rings? So the answer to this question, surprisingly, is not as well known. In fact, we couldn't find any place in the literature which gave a complete answer to this question. So, and anyway, I will tell you how we came about this, but first let me go ahead and solve this question.
Sorry, 1 second. I mean, Z mod Z is a finite commutative ring for all n, right?
So what is it?
Z mod NZ is a finite commutative ring for all n, right?
Oh yeah, so okay, so actually, thank you for, see, my brain is not working already. I'm tired, I can tell. I forgot to put the stars here. So otherwise the problem would
now the first,
and now you need to say -1 in upstairs.
Yeah, so prime power -1. Okay.
1 less than
is a prime power -1. That's correct. So if you have a finite field, the number of so we're talking about the number of units here. So and R star is, what is R star? So let's examine this question. So, or more generally, you can talk about any commutative ring. So if you have any commutative ring, how many units can this have? So let's look at the case when the cardinality of R star is even. So if R star is even, so let's say this is equal to 2m. So in this case, I can actually write down one example and then I'll be done. I can give you a ring which has exactly even number of units. And there are many examples you can take. So you can, but the one I'm going to give you is this one. So take R to be the polynomial ring Z adjoint X mod X squared comma mx. So this is a ring, and every element in this ring is of the form. So every element in R is of the form A plus bx. So where A is an arbitrary integer, and 0 less than or equal to b less than or equal to m minus 1. Okay, and this becomes a unit. So A plus bx is a unit if and only if I can say that A times A is an invert, A is a unit if and only if A is either +1 or -1. You can actually show that. So in this case, you can actually show that R star is isomorphic to C2 cross Cm. So this is an example of a commutative ring. It's a finite commutative ring which has exactly 2m elements. So R star is 2m. Okay, so that is good. Now, what about R star odd? So given any odd number, can you give me a commutative ring which has exactly odd number of units? So here the answer is more surprising. Well, we'll see how. So first off, I'm going to make an observation. So let G be a finite abelian group of odd order. So if R star is equal to G, so the set of units in the ring is G, which is a finite abelian group, because R is a commutative ring. So R is a commutative ring. Then R star is G, and a finite abelian group of odd order. So we know that then I can write this R star as as a product of cyclic groups C P1 to the alpha 1 cross C P2 to the alpha 2 cross C Pk to the alpha k. So it's a finite abelian group, and here I'm looking at odd case of all the PIs are odd primes. PIs are odd primes. Okay, now I first begin with the observation that the characteristic of the ring R has to be equal to 2. Why is that? Why should the characteristic of R to be 2? Because
the characteristic here, it's the sum of the minimum number of ones you add to get 0. Yes,
correct. Yeah. So the characteristic of R is so is the minimum, so the smallest number of ones you should add to get 0. If there is no such thing, then the smallest integer you say it's the characteristic will be 0 here. So if the characteristic of the R has to be 2, why? Because -1 should be equal to +1. Otherwise, -1 squared is equal to 1. So this implies there exists an element of order 2, which is impossible in a group of odd order. So this means -1 is an element of order 2. Order 2. And that is a contradiction. You cannot have an element of order 2 when you're starting with a group which is an odd number of elements. So therefore, it has to be a characteristic 2. So which means the field of 2 elements sits inside R. There's a natural map because it's a ring of characteristic 2. So characteristic.
You can say that fact was first proved by Lagrange. Since you recall Galois, you can recall Lagrange here.
Oh yeah, that's right. So this is by Lagrange. Yeah, so F2 embeds inside R, so it's a field of characteristic 2, and then So let's say if you have generators here, G1, G2 up to GK, these are the generators, then there will be a natural map from the polynomial ring XK to R, which maps XI to GI. And this is standard, and then this factors to the quotient map. So this map goes through the quotient. What did I get? Call it alpha 1.
Sorry, alpha 1.
Yes. Pk to the alpha k minus 1.
Sorry, xk. Sorry, not xp.
Oh, yeah, right. Yeah, xk to the alpha k. Thank you. I'm glad Apurva is catching all my typos and mistakes here. So you have this quotient because these elements have, these are cyclic groups, and each GI has order pi to the alpha I, so you get through this quotient. Okay, I'm just looking at the chat here. So somebody said something. Okay, I can hear him. All right. Okay, good. Now, note that this thing is also isomorphic to the tensor product of these fields F2 xi mod, let me write this one carefully, xi pi to the alpha I minus 1. So you take a tensor product of these things, I running from 1 to k. All right, so this is all good. Now notice something here. So this now you have this tensor product. Now here I didn't mention one thing, but without loss of generality, so without loss of generality, we may assume that R is generated by its units. Otherwise, you just take the subring. Otherwise, you take the subring generated by the units. Then that will still have the same unit group. So this, I'm going to assume that R star R is actually generated by units. So that is more than just saying that R star equals Z. Yeah. So you just take the subalgebra over F2, which is generated by the units. That will be a smaller ring, presumably, and then that smaller ring also has the same unit group. Okay, so now you have this one. Okay, good. But now this polynomial, if you look at this polynomial, this has a factorization over F2x. So the claim is that the observation is that these polynomials, the polynomials xi to the pi to the alpha I minus 1 split as a product of distinct irreducible polynomials. Split as a product of distinct irreducible polynomials. So this is a unique factorization domain I'm working here. So these polynomials, distinct irreducible polynomials. And why is that? Well, that is because if you take this polynomial and you take its derivative, they're co-prime. Working mod 2, okay, over F2. So these things will be, so whenever a polynomial and its derivative have no common factors, so then it actually splits as a product of distinct irreducible polynomials over F2x. Okay, so then by the Chinese remainder theorem, so this one is F2 xi over xi to the pi to the alpha I minus 1 is further isomorphic to F2xi. So this splits as a Cartesian product of Pij. So this is the decomposition of this polynomial into irreducible polynomials. Yeah. So these are, this polynomial may not be irreducible, but these will be irreducible. So what is the conclusion? These are all finite fields of characteristic 2. So this is isomorphic to a product of F2 to the power of theta ij. Because this is a field of this is a polynomial ring f2x. When you reduce it with irreducible polynomial, you get a finite field. So that is what you have. Okay, and now a tensor product of this kind of distributes. So this whole thing, so this conclusion is that the tensor product of f2xi so this will be some grand product of finite fields of characteristic 2, finite fields of characteristic 2. Now, finally, R itself will be a quotient of a product of finite fields. So we know that every quotient of a product of finite fields is again a quotient of product of finite fields of possibly fewer factors. So this tells you by the first isomorphism theorem or otherwise. So let's call this map phi. So when you go, I'm tired of writing this one. Let me call this S. S mod kernel phi is isomorphic to a product of finite fields of possibly fewer factors. You might drop some factors when you take a mod by an ideal finite fields of characteristic 2. So the upshot of all this stuff then is that when you take the units on both sides, so when you take the units on both sides, what you get R star is isomorphic to the product of finite fields of characteristic 2. So that means it's a product of cyclic groups of order 2 to the power of something beta R minus 1. So what is S? S, I said I'm tired of writing this all the time, so I just call this S here. Okay, you have this one. So, so the upshot is that if you have a finite abelian group, which is the group of units of a ring, it has to be this one. So, and note that this is going to be an odd number. So the observation then is that an odd number, so the upshot of all this is, the upshot of all this thing is that an odd number is the cardinality of the number of units of a commutative ring if and only if it is of the form product of 2 to the power of beta R minus 1. So over some finite numbers. So the only odd numbers you get are these things. So here, when I did the even case, we picked every even number as the cardinality of a unit group. But when I came to odd, so this computation shows you that it's this one. Okay, so these are all the finite numbers and odd numbers and even numbers. And for infinite cardinals, what about infinite cardinals?
So due to whom is this result?
Oh, this is all my work recently that appeared. Yeah, probably. Actually, I should thank you. I should have mentioned that. So this is all joint work with Keir Lockridge.
So the converse is straightforward. Is it the same step?
Yeah. So converse is straightforward. If you have these numbers, just take finite fields. You know, product of finite fields.
Oh, just take the product itself. Yeah, sure. Yeah.
Right. So for the infinite cardinals, it's very easy. If lambda is any infinite cardinal, lambda is any infinite cardinal. So let S. Let's not use the word letter S because I already used S. I don't know. Let T be a set. T be some set. So that the cardinality of T is lambda, then you just take F2 of T. So this is the field of all transcendental functions with variables T. So this is the field of rational functions in variables, with variables from T. So then using transfinite arithmetic, it's not hard to show that this has cardinality equal to lambda. Okay, so that gives, that is now a complete solution to the following theorem, which appeared in the American Math Monthly. So with myself and Lockridge. So let lambda be a cardinal number. Any cardinal, finite, infinite number. There exists a commutative ring R with R star equals lambda if and only if lambda is one of the following. Well, I just have to pack all the things I told you. So one, any odd number of the form product of 1 less than powers of 2, some finitely many. 2, any even number. So there are no restrictions on even numbers. All even numbers were realizable. We already gave any even number. And 3, any infinite cardinal. Okay, so what I gave you now is the full proof of the theorem that we published in the American Math Monthly, right? So again, let me go back to this thing here. So what positive integers are units of finite fields? Well, it's 1 less than prime powers. That's well known. What about finite commutative rings? Not so well known. I mean, at least if you dig up, if you collect all pieces in the literature, you might find a result, but it's nowhere written down. So we thought we should write this up. And it's a simple thing that you can, even any first year algebra student can understand. And so first, are there any questions on the computation or the statement of the main result here for realizability of numbers as orders, cardinalities of units of commutative rings?
Actually, I want to clarify one thing. Can you just go up to the even case?
Yeah. Yeah.
So I was trying this. I think I might have gotten the computation wrong, but let's say M is 1. Oh, never mind. Sorry, I got it wrong. Yeah, I was reading it wrong. Sorry.
Yeah, so this is, I think there are other examples too for even numbers you can pick, but here for any positive integer M, so this one will have this Cartesian product as the
R star here is even is 2m, right?
Yeah. R star cardinality is 2m.
No, I mean upstairs you wrote it's 2n. But yeah,
yeah, right, yes.
The other thing was I had a question on in the result.
Yeah.
In the theorem, do you also, whether in the theorem or outside it, do you also, can you also provide some kind of, I don't know, sharp or non-sharp upper bounds on how big the ring itself must be for a given cardinal to be the size of the unit set?
How big the ring has to be? So let's see.
How small it can get, kind of thing.
How small it can get.
Clearly, for a single 2 to the power ni minus 1, the answer is 2 to the power ni. Or, or p power alpha minus 1, the answer is p power alpha. But
yeah. Right. Let me see. Do I know the answer to this question? No, I don't know. Yeah. So though I don't know. So basically, you are asking, can we bound this quantities, right? So can we bound this quantity R minus R star somehow?
That's right. Yeah. Effectively or ineffectively or somewhere.
Right.
Yeah.
Okay, yeah, so no, that's good. So, that's the reason why we should give talks. We get some interesting questions from the audience.
Yeah.
No, we never thought about that. Okay, so that is a good question. So I want to record this question. So can we bound, so good question, Apurva. Can we bound R minus R star? So yeah.
I mean, there may be very large, also, yeah, actually, maybe, yeah, can you find very large rings with this size or very small rings with this size? Maybe both questions might have some, lead you to some interesting findings. I don't know. Yeah.
Yes. No, this is an interesting thing to look at. We haven't looked at. Okay, so.
Yeah, I had one question. This example that you have given for even, that's an infinite ring, right?
Yes.
So
Yes.
is there a finite ring which has even, I mean, or did you answer that? In
so are you talking about, wait a second, let me make sure I'm
ZX?
So
Above.
That's right. So this one, right? So this
yeah,
one,
yeah.
So this is right.
Because the constants embed in it, right? So.
Yeah, right. So can you get a finite commutative ring? So that I don't know. So
okay.
That I don't know. Yeah, good.
Okay.
I don't know.
Okay. I just want.
Yeah. So that's why in the theorem I said there exists a commutative ring. I didn't say it's a finite commutative ring, but you can also ask this question for finite commutative rings.
Yeah, I understood that. Yeah.
Thank you, Suresh.
Yeah. Thanks.
So you think that's
and in fact, I think I should look up my notes. This I might have another example. I have to think and get back to you. So this was actually the second. So in the initial research, we had a different example, and then later we realized that this is much easier to write it down. So we actually switched to this example. Now I'm trying to recall what was the other example. We had a different example. I wonder if that was actually finite. But anyway, I had to think and get back to you. Okay, are there other questions?
Should we know anything about the number of different rings in the odd case at least? Or are there? I mean, your proof pretty much said that we must proceed in this way. It was pretty forced.
Right. Yeah.
Can there be many?
Yes, that's right. So in fact, there is actually more you get from the proof. So not only the order of the unit group, but it also tells which unit groups you get. So the only unit groups you get are product of cyclic groups whose orders are 1 less than powers of 2. So those are the only groups you pick, and that follows from the analysis of the thing that I just proved. So, and that is actually leading to the next topic that next thing that I want to talk about.
Oh, but those things don't have to be primes, right? Those 2 to the ni minus 1.
No, they don't have to be primes.
Numbers which are products of
Yeah. So at this point, I gave a complete answer with full solution to the question: how many units can a commutative ring have? So we answered this question. So at this point, I can say my talk is over. But as I said, this was an offshoot of a bigger line of research, which is what I want to talk next. And in fact, so that is Fuchs problem. So sometime in the year 1970, so Laszlo Fuchs asked this question: which abelian groups occur as the group of units of a commutative ring? So from the category of commutative rings to the category of abelian groups, there is a functor which takes a commutative ring and associates to it the set of all unit groups. So that is a functor. Now it's asking which abelian groups can occur as the unit. So like you can have from the category of commutative rings to the category of abelian groups. And so which ones will be realizable here? So what we just answered, you can think of that as a weaker version of Fuchs' problem. So you further go with the cardinality to the cardinal numbers. So a ring R gets associated to its unit group. This gets associated to the cardinality of this one. So we actually, so the about theorem here, you can think of that as identifying the image of this composite function. But now what Fuchs asked is, can you tell what is the image of the first function? Okay, so Fuchs asked this question, and there is no reason to restrict to abelian groups and commutative rings. You can also ask for which groups occur as the group of units of any unital ring. So that can also be asked. That's the more general version of the Fuchs problem. Yeah. And this is a problem from 1970, and there is not much. There is some results known. I'm going to tell you what was known and what we added to this knowledge. The first known theorem in this came right away in actually this Fuchs problem. Let me write down the year. Is it 1960 or 1960? Yeah, this is 1960. And in 1970, the first theorem came, which was due to Pearson and Schneider. So they answered this Fuchs problem for the class of cyclic groups. So the theorem they proved is the following: a finite cyclic group Cn is realizable as a group of units of a ring it's actually a beautiful result, actually. If n is a product of a pairwise relatively prime numbers, relatively prime integers taken from the following list. So it should be either 1 less than a power of a prime. So Q is a prime and T is at least 1, or it is Q to the S times Q minus 1, where Q is an odd prime, two times 2h plus 1, or 4 times 2h plus 1. So that's a technical condition. H is greater than 0, and every prime dividing 2h plus 1 is of the form 4k plus 1. Anyway, so these are some number theoretic restrictions. So now, using this theorem, give me any positive integer n, and I will be able to tell whether the corresponding cyclic group is realizable as a group of units or not. Well, it's a very clear and descriptive. N should be a product of pairwise relatively prime numbers, relatively prime integers, and these things should be coming from these baskets. Okay, so it's very descriptive, very, very simple. And now, after this, a simple question is that because every finite group, abelian group, is a product of cyclic groups. So can we not complete the problem for finite abelian groups? So why that turns out to be a wide problem, open problem. So this one, answering this question for answering Fuchs problem for finite abelian groups is wide open. In fact, to my knowledge, so this is the hardest case. So yeah, every finite group is a product of cyclic groups. And we know the answer for cyclic groups. So one might think that, yeah, just somehow patch these things and get the answer for finite abelian groups. No, it's not going to work that way. It's actually very, very, very non-trivial result. Yeah. So to just, again, to give a flavor of this one, maybe I can, again, run through one calculation which you'll be able to follow this. So I'm going to, so there are many proofs of this one. This one is follows from one of our own results, so the theorem. So let P be an odd prime. So then the cyclic group of order P is the group of units of a ring if and only if P is a Mersenne prime number. Okay, you can actually take it, take this problem, and you can actually try it. You can, using the similar kind of tricks I've done earlier, you can give a proof of this one. So maybe I'll sketch the proof. I will not go through all details like I did earlier, but I'll just proof sketch. Again, like I said earlier, it's an odd prime. So CP is an odd group. So this tells you that if CP is R star, then the characteristic of R again has to be 2 by the same reasoning I told you earlier. So the characteristic has to be 2, so which means, again, I can get a map like this. There is a natural map R, which, so here X goes to the generator G, which is G to the P is equal to 1. So then you have this quotient map right here. And this has an interesting factorization, the cyclotomic polynomial, X to the P minus 1. You have this factorization. And again, this splits into product of distinct irreducible polynomials. So I can write this map phi as a product of f to x mod pi of x going to R. And again, this is a product of finite fields.
Maybe we can call it fi of x. There's a p involved.
So what is that, fi?
Yeah, x to the p minus 1. That's just so not to use p. That's all.
Right. Yeah, that's right. Yeah, I should be doing that. But I'll just move on to this finite fields.
Then it's fine. So.
Yeah, so you have this going this way. You have this finite fields, right? Now, again, you can go modulo the kernel. So you go phi modulo the kernel of phi. So that gives you a product of finite fields which embeds into R, which picks up all the units. Now, when you take the units on both sides, so this tells you that the product of cyclic group, so these are finite fields, the multiplicative group is a cyclic group with one less than the cardinality of the finite field. So this one embeds into R star, but R star is CP. And now by the structure theorem for cyclic groups, this tells you that 2 to the ni minus 1 is equal to P. So that tells you that P is a Mersenne prime. Okay, so, and already you can see the subtlety of this problem. So you know the answer for cyclic groups, but I'm saying that this is wide open for finite abelian groups. So again, to illustrate this one, let's look at a C10. Well, that is a realizable because this is the set of units in the field of 11 elements. But C10 is C2 cross C5. But C5 is not realizable. There is no commutative ring out there whose unit groups is C5 is not realizable because 5 is not a Mersenne point. So this tells that once you know that A cross B is realizable, that doesn't mean that the components themselves are realizable. So that is what makes this problem a very hard question. So, but what we were able to do is that in joint work with Lockridge, we proved this problem for the class of indecomposable abelian groups. In fact, this is our first result which appeared in the Journal of Algebra, some 2015, so theorem. This is with Lockridge. So this is basically a solution to so let me write that down. Oh, it says my connection is on. So the theorem is an indecomposable abelian group. So when I say indecomposable abelian group, it's an abelian group which is cannot be written non-trivially as A direct sum B, right? So it's a direct sum indecomposable abelian group. Is realizable and I should start using the word realizable instead of saying is the group of units of some ring. I'll just say is realizable if and only if it is C2, C4, C8, CP, P Mersenne, and CQ minus 1, where Q is a Fermat prime. And G, any indecomposable, torsion-free abelian group. So this is a full classification of all indecomposable abelian groups that are realizable as group of units of some commutative ring. Okay, and the main theorem, it will be too much to write down the main theorem. In fact, our main theorem is stratified by the characteristic. So in other words, we don't not only give the list of all groups which are realizable, we also tell which groups are realizable in every single characteristic that can possibly occur. So let me show you that. So here is that paper, Fuchs problem for indecomposable abelian groups. So let me go right to the, so this is the theorem that I'm trying to draw your attention to. So if you look at the, so basically what I listed is the union of all these groups, but the more refined version is if you have a ring whose unit group is indecomposable, then first and foremost, the characteristic of that ring has to be 0, 2, 4, 3, 6. Q or 2 times Q, where Q is a Fermat prime. And moreover, in each group, in each characteristic, these are the groups which are realizable. And in the third column, we give a ring whose unit group, we give an example of a ring that realizes that group in that characteristic. So I think one thing that is interesting to note, for instance, you look at cyclic group of 4 elements, right? So that is realized in characteristic 0 as the units of the Gaussian integers. It is realizable in characteristic 2 as units of this truncated polynomial algebra, f2x mod x cubed. It is realizable in characteristic 4 as units of this quotient ring, z4x mod x squared minus 2, 2x. and nothing else. Yeah, so I think this is, in some ways, this is the best possible answer to the Fuchs problem, because it's actually a stratified version, more than what Fuchs was asking for.
But those are not all the realizations, right?
But those are not what?
He's saying C4 does not occur in the last two rows. C4 cannot occur in the last two.
That's right. C4 cannot occur in the last two rows, but we don't know that in characteristic 2, could there be some other ring whose units are C4, or there could be some infinite.
I think he says,
ring,
yeah, we give an example of such a ring.
Yeah.
This is an example. Yeah. So in the third column, we give an example. We are not saying that this is the class of all, and in fact, it's not, because if you take any ring, you can always take Cartesian product with F2.
Okay. Yeah.
So that is going to give you a non-isomorphic ring, which will not change the unit. Okay. Any rate, but I think what is noteworthy here is this last one, and that is there is no commutative ring whose unit group is a quasi-cyclic P group, which is Cp to the infinity. What is this one? This is, I defined it here. It is the union of Cp to the n, p greater than or equal to 0. N greater than or equal to 0. So you take the ascending union of the powers of Cp to the n. So that is an example of an indecomposable infinite P group.
Is that called the Proofer group or something?
Yeah, so I think I probably mentioned this somewhere here. So yeah, that's right. There are other names for this one. It's called the Proofer group, I think. Yeah, you're right.
But it's an inverse limit, right? Not a direct limit.
Yeah, it's an inverse limit.
Yeah.
Okay.
QP mod ZP.
Oh, what is that?
QP mod ZP.
Yes. That's right. Anyway, so that is our first result, and the proof is so long, and I mean we don't use any high-powered machinery, but it's kind of tedious and it's long, but it involves similar ideas that I am showing you here. Yeah. So that is what we did. This was done in 2015. And a year later, we proved a second theorem, which appeared in the Journal of Pure and Applied Algebra. So this is again with Lockridge. He was a good old friend of mine from graduate school. So we go back from 2000, Seattle. Anyway, so this is where we answered this Fuchs problem for dihedral groups. So the question is that which dihedral groups can occur as the group of units of some ring? Of course, this time it's not going to be commutative because the dihedral groups are non-commutative. So, and we gave a complete answer. So this was very satisfying. A dihedral group, the group of symmetries of a regular n-gon, dihedral group is realizable again, realizable as a group of units of some ring if and only if it is D2. Well, I guess that's the not boring example. So D4, D6, D8, D12, D4K.
By the way, just to clarify, Dn has size 2n, right?
So Dn has size, actually, no, Dn has size n in my notation.
N, okay, okay, good to know. Okay.
D2 would be,
What is that?
yeah, no.
Yes.
C2 is Z2 with S2. You can put two other letters, or C2 also, and so means notation.
That's right. So, so let's see what I was going to say here. Yeah, that's right. So these are these are, so in particular these.
Sunil, you omitted at least D8 and D12 probably. Okay, fine.
I could have what?
Omitted D8 and D12, right? If there are no restrictions on K.
If there are no restrictions on K, so yes, good question. So there are restrictions on K. Actually, I haven't finished the sentence, I guess. So
okay.
K is odd. And so, so you have, and these are, well, forget about D4K for a moment, but D6, D8, D12, these are the non-abelian ones.
What do you mean by no?
So the other example.
What? Everything is non-abelian. D4K is, I mean, everything bigger than D4 is non-abelian, right?
Yeah. So in this, so in the list that I got here, D2 and D4 are abelian, D6, 8, and 12 are non-abelian.
Oh, sorry, you're saying forget the D4K. Sure, yeah.
Yeah, forget about this for a minute. So these things are non-abelian, and I will tell you why we have to forget this for a minute. So you will see that. But these three are non-abelian ways, and this turned out to be very surprising because if you keep aside these abelian ones, so these turn out to be exactly the symmetries of polygons which tile the plane. So the only regular polygons you can tile the plane are equilateral triangles, squares, and hexagons, which have symmetries D6, D8, and D12 respectively. Okay, and just like we did this theorem, our theorem here is also stratified by characteristic. So let me show you that. So this is the one which appeared in Journal of Pure and Applied Algebra. So here is the full classification. If you have any dihedral group which is realizable as the group of units of any ring, the characteristic of the ring has to be 0, 2, 3, 4, 6, 8, or 12. And this is the D4KK, or this is the only case where you pick infinite rings. In every other case, you pick finite rings. And in each characteristic, we give you the list of dihedral groups which occur in that characteristic. And in the third column, we give an example of a ring whose unit group is that corresponding group. So it would be an enlightening exercise for students to take this column and compute all these unit groups and see that you get these rings. And that is the reason I'm saying that let's forget about D4KK odd, because if you ask what are all finite rings, then this one is off the chart, because this will be characteristic 0, which will be an infinite ring. And the finite rings will be coming from this case, and the interesting ones, keeping aside the abelian ones, the non-abelian ones correspond to symmetries of polygons which can tile the plane. Okay. Yeah. So this is another super technical paper. I will not have time to go over that, but that is the result we proved. And then I think a year later, again with Lockridge, we answered this question for quaternion groups and dicyclic groups and almost cyclic groups. So for a whole class of families, we answered this question. I mean, I'm not going to pour all the results here, but I'll just mention that Q8 turned out to be the only quaternion group which occurs as the group of units of a ring. So when we first investigated, we looked in the literature. So there was already one known ring whose unit group was Q8. So, you know, the quaternion algebra or something. And then we thought, okay, what about other generalized quaternion groups? So it turns out that none of the higher generalized quaternion groups, so in the entire family of Q2 to the n, only Q8, n at least 3. So these are the generalized quaternion groups.
Sorry,
what is that?
What is Q2 to the n?
Oh, so this is a group this is a group of order 2 to the n, which has a big cyclic subgroup. Of index 2, and you can write down relations if you like, generators and relations. You can write down the generators and relations for this one, x2 to the n minus, so this is a group of order 2 to the n minus 1 equals y squared equals 1, and then I think so something like conjugation by what yxy is something I forget what it is.
N minus 1. Sorry. Okay.
Yeah, so this is a generalized Quaternion group. It's a group which is generated by 2 elements. It has a cyclic subgroup of index 2, and so you can actually, I don't remember the exact relationship between x and y, so you can look it up. So this is this will be q2 to the n.
Would you call it a metaplectic group, Amri?
What is that?
I was asking Amri if he would call it a metaplectic group or something.
Why?
Some kind of a C2 cover of, or a
like that.
cyclic cover of a nice group. Sorry, go ahead.
I mean, there are names for this in the literature.
Right?
So these are called, I think, almost cyclic groups, because they have, I mean, up to this index 2, this is almost cyclic. So there are other names for this one. So basically extensions of C2 minus 1, C2 to the n minus 1 with C2. Okay, I'm almost out of time, but I think I will end with one result, which I always think that it's a very interesting one, because it actually goes back to Gauss. So we proved all these things, and I think the troublemaker is always the 2 groups, because for odd groups we have a good understanding. For 2 groups it was always a challenge, but we were very amused when we proved the following theorem. There exists a 2 group. A 2 group is a group whose cardinality is 2 to the power of something. In characteristic 2, in characteristic n.
You mean realizable in characteristic n?
There exists a 2 group that's realizable in characteristic n. That's right. There's a 2 group that is realizable in characteristic n if and only if, okay, it is possible so this is one of the classic things, to construct a regular n-gon with straight edge and compass.
Okay, that is very nice, very nice. You're saying there are only, okay. And the proof of this actually goes to some kind of similar, like quadratic field theory or whatever.
Okay, so very good question you're asking this. I just presented in a way that you would appreciate, but actually the proof, we use Gauss-Watzel theorem. So this actually, what we actually show is that this thing is equivalent to if and only if n is of the form 2 to the power of a, p1, p2, pk, where pi's are distinct from our primes.
And that is by some sort of more technical analysis, like in your papers, other papers.
Yeah. So yeah. But everybody can follow these things. This is
sure. But
yeah, distinct from our primes. And of course, this one is the Gauss-Watzel theorem. And it's kind of interesting because we start with this problem of Laszlo Fuchs, which seems somewhat esoteric, and you make a connection to something which is more classical. So anyway, so I think I will end the talk right there. So thank you for your attention, and sorry for all the mistakes. This is way past my bedtime to think more coherently.
Thank you so much, Sunil. This was a wonderful talk. thank the speaker, I guess. Questions, more questions rather. Yes.
I just have one small question. So you said that there exists a two group that that is realizable in characteristic n. So can we determine what the cardinality of the two group might be?
Can we determine what the cardinality of the two group?
Or to refine it in again upper and lower bounds of some kind.
Yeah, let me think.
Sorry, I just had that thought.
Right. So no, actually, our proof does not give you that. So if you have a two group that realizable in characteristic n, so we work more with the ring of So basically, actually, actually now that I'm thinking about it, so this proof is not hard actually. Now I'm thinking about it. Yeah, it looks very impressive, but actually it's not hard, because if you have so there exists a two group in realizable and characteristic n. So let's say G is the two group. G is a two group realizable in characteristic n. So then first and foremost, so there is a ring R, so that R star equals G. And then it is a characteristic n. So Zn should be a subring of R. So this means Zn star is a subgroup. This Zn star should be a subgroup of G. So which means Zn star is a two group. Zn star is a two group. But now this is an elementary exercise in abstract algebra. We know what Zn star is, and you write down, and then some elementary number theory and all that calculation will show you that. In fact, we can actually do it right now. So it's not hard. So let's take a prime factorization 2 to the a. So p1 to the alpha 1, p2 to the alpha 2, dot 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 pk to the alpha k. So there are no restrictions on 2 to the a. So I keep that. There are no restrictions. Now, all I have to show that this higher exponent should be 1. Well, that's also easy by the Chinese remainder theorem. Zn is the Cartesian product of z 2 to the a cross z p1 to the alpha 1 dot dot dot. And then when I take the units, you have this one. So the units of z pi to the alpha I, what is that? So the order of that is the Euler phi function of pi to the alpha I, which is pi to the alpha I minus 1 times pi minus 1, if I remember correctly. So that is the Euler phi function. And this guy should be a two group. If this guy is a two group, this has to be 0, which means the alpha i's have to be 1. And this should be a power of 2. That means if pi minus 1 is a power of 2, that means pi should be 2 to the power of something plus 1, which means pi is a Fermat prime. Okay, and actually there is a little bit more to it, but essentially that is the idea. So as you can see, this is not hard, but this does not tell you, I'm not answering your question, but I'm just telling you that the proof does not give us any control on how big the size of the realizable group is, because you're working with Z mod n. Yeah, but that's a good question.
Actually, yeah, I just realized you proved the whole theorem. I mean, it's not. Again, it looks so simple.
Yeah, it is simple. It is simple. Yeah. So a lot of the arguments in these papers are like this that we wrote. It's a clever assembly of little things here and there, and you get some interesting answers for it. My personal favorite is the one we published in the American Math Monthly, which is what I proved at the very beginning of the talk. So where we gave a complete answer to a question. This is a question that you could have been asked right after you tell students what a commutative ring is. You can ask this question, and to my surprise, this is not as well known, but so that is why we decided to publish this paper in a journal which is most widely read in mathematics journal in the world, and that happens to be American Math Monthly. So So which is a fact I learned recently. It is the most widely read mathematics journal in the world. Anyway.
Very nice. More questions, more questions.
What about the infinite dihedral group?
Infinite dihedral group. Yes. Yeah. We worked on that infinite dihedral group, and we have some results there, but we don't have a complete answer. So what results we have? So for instance, if the infinite dihedral group is realizable, then we can say something about the underlying characteristic. So, but we couldn't go further from there, Yeah, so that is a good question. Yeah.
So there are also like infinite abelian 2 groups, 2 torsion groups. Like, I think there's a classification theorem for certain classes of these, Alms Theorem. And so you get into this whole world of infinite abelian groups, for which I think Laszlo Fuchs is very well known.
Yes.
So is it, do you think, have you tried those? What are they called? I think there are.
So I mean, that something like that came in this paper that I showed you, right? So this one. So we let me show you this, kind of related to what you're asking. Where is this now? Yeah, torsion-free groups.
Torsion-free. Oh, okay.
So torsion-free. So in the case of torsion-free, so we were able to show this. So this is the theorem we prove in the torsion. G is a torsion-free abelian group, and these are like the notoriously hard classes of abelian groups. The torsion. This is always the hardest one. To the point it actually becomes really some crazy set theory after a while. It's not algebra. Anyway, if G is a torsion-free abelian group, then you just look at the group algebra of the torsion-free abelian group with coefficients in the field of 2 elements. We are able to show that the units in that group is isomorphic to the group G.
Oh,
yeah.
Okay.
Yeah, so every torsion-free abelian group is realizable. And in fact, actually, if I remember well, we first started this with the rational numbers. So if you take the additive group of rational numbers, it's a torsion-free abelian group. So I asked, is there any ring out there whose unit group is the ring of rational numbers? I was searching, and then it occurred to me that the simplest thing, just take the group algebra over the field of 2 elements, and that is what you need. And
yeah, I was thinking more like 2 torsion groups, infinite 2 torsion groups.
Yeah, infinite 2 torsion groups. Yeah, that is that. For what about the Pruford group?
Yeah.
So that is 2 torsion, right?
I'm trying to remember. There's something called Alms Theorem, which is a classification, which is a generalization of the classification of finite abelian groups, which is for a certain family of p torsion groups, reduced 2 torsion groups.
Yeah, I don't know about that, but this is the closest thing that comes.
Interesting.
CP infinity. So this is an example of an infinite 2 torsion group, and we've shown that that is not realizable as a group of units of a ring.
So take a look at this class of reduced 2 torsion group.
Yeah.
That may be interesting.
Yeah. So, after a while, we got to the point that, so we picked up all the low-hanging fruits in this area. So, and then anything further would require some quite heavy lifting. But of course, we are willing to do that, but we are running out of ideas here.
Yeah, I have a question then.
Yeah, sure.
You talked about dihedral groups. So how about permutation groups?
Oh yeah, so yeah, a very good question. Yes, so this is well known. Actually, I didn't do that, but that's completely solved. So in fact, this is solved for all permutation groups. It is solved for all the class of all finite simple groups. Everything is done. So if you want to know for, so I can tell you exactly what is known for this. So maybe at some point I should write an expository paper on Fuchs to explain people what is known and what's not known. Yeah. So to answer Apurva, to answer your question, so here is the answer. Let me write this down. So the only finite, symmetric, and alternating groups that are realizable are S1, S2, S3, S4, A1, A2, A3, A4, and A8. So this is the result of Davis and Occhipinti from the year 2014, I believe. Yeah. And when you look at finite simple groups, the answer is very simple. Now, the only finite simple groups, which what group theorists love, I guess, finite simple groups that are realizable are cyclic group of order 2 elements, cyclic group of order p elements, p is a Mersenne prime, and PSLF2, n at least 3. That's it. Nothing more, nothing less. No. So this is the class of all finite simple groups. I mean, we have a full classification of finite simple groups, I guess, and this theorem does not use the classification of finite simple groups, but it's again, this is also by Davis and Occhipinti from, I don't know, 2014, 15, shortly before we started our work. So they have a full classification. Finite simple groups.
Very fascinating. So yeah, S4, yeah. S4. So, and they don't link it to Galois, I guess, like you linked it to Gauss. But okay, the reason I was asking about this was not actually finite simple groups. My thing was coming from what is something closer to what Amri and I maybe are interested in, which is commutative groups. Which commutative groups are realized? Finite commutative.
Yeah. So you can ask. Yes, you can ask this problem for any class of groups. So this is what we did, and after that we got tired of it. We thought we should move on to something else, so we were doing something else. But actually, I recently posted a paper on the archive, which I taught a course on. We have a course here which is called, which is equivalent to something called graduate introduction to graduate research in mathematics. We have one introduction to undergraduate research and the introduction to graduate students. So in this course, graduate students get to do research. So we did a research and we actually published, we wrote a paper, it's up on the archive, where we did the reverse problem. So there you fix a group and ask what rings have that unit group. So we did that one. For instance, this is where the combinatorics is coming. So the problem which I worked with my students, is the following. So what are all, let's say, finite what are all rings are such that R star is just let's say a simple elementary abelian 2 group. So can you give a classification of all rings R for which the unit group R star is an elementary abelian 2 group? So I think we made good progress on this. We answered this question for all finite dimensional algebras, for all path algebras, for all matrix algebras, for all finite rings. So for a whole class of rings, we answered this question. And so one thing we ended up working in the process, this is where the combinatorics came in. So this is, I remember I was telling that if I have time, I would go into the combinatorics. So this is, so x1, xl, x1 squared, x2 squared, xl squared. So look at this ring. It's a very simple looking ring. You take the truncated polynomial ring in L variables, where you mod out with the relation xi to the power of L for all I running from 1 to L. Now, we had to look at all possible quotients. So the question is, can you classify all quotients of this ring? And I asked like some experts, asked Dave Benson, John Carlson, Richard Stanley, and Shrikant Iyengar. So covering areas of representation theory, combinatorics, algebra, and everything. So this is a problem to turned out to be very hard. So they all thought it was an extremely hard question. And this problem is, our classification is based on quotients of this one. And this has to deal with some free distributive lattice on some generators. And even we wrote some programs in GAP to compute those numbers. And these are really pretty wild. So computing the number of isomorphism classes of this quotient. Yeah, so here's a simple number. So let's call it a lambda L. For every positive integer L, lambda L is the number of distinct isomorphism classes of quotients of this polynomial algebra, truncated. So this turns out to be an extremely mysterious number, and only, in fact, John Carlson told that he can only compute this for L equals 1, 2, and 3 maybe. And beyond that, there seems to be no hope of computing this. And there is some interesting combinatorics related to that problem.
So what is it for L equals 2?
What is that?
What is the answer for L equals 2?
What is the answer for L equals 2? Oh boy, I don't remember.
Never mind, it's okay.
No, I should look up. I mean, I don't think he gave me the answer for L equals to 2. And so I think using GAP, the answers we got for, I'll tell you, for 3, 7, 47, 4,979. And then something like that. So this is some wild sequence. We don't know. We don't understand this very well. Yeah. So for L equals 2, you asked, right? So for L equals 2, I can write this down. So 1. So for L equals 2. So what are we looking at for L equals 2?
Look at OEIS and it didn't give you anything here, or when you add 1 to all of these numbers, it didn't give you anything.
I remember putting that. I don't know if I don't think I got anything here. So for L equals 2, you have this distributive lattice x1, x2, x1, x1 plus x2. So it's kind of monomial ideals here. x2, x1, x2, the product x1, x2, and 0.
That ring itself is the ring of all multi-affine polynomials, right? Because there's no repeated degrees, so the ring is dimensional with 2 power L.
Multilinear.
Multi-affine, because you can have x1, x3 plus x3 plus x1.
Yes.
Okay.
So the reason I'm saying it is because multi-affine polynomials, there's something about real stability and so on where these polynomials play a nice role. Anyway, that's a completely separate context.
So
yeah. So, but anyway, so this
ideas,
is like,
and the answer is just okay.
So you have, I think, how many counts? Is it 7? 1, 2, 3, 4, 5. Yeah, 7. So that is for x1, x2, I think. So these are the Hasse diagrams for the poset of ideals for L equals 2, and then. So the actual number of quotients is at least so this is like a free distributive lattice on L generators. And the number of quotients I'm looking will be more than that. So because this is all just by looking at the monomial ideals, but I can have more crazy quotients here. So anyway, this, I don't know anything about it, but our classification of rings whose unit group is an elementary abelian 2 group is based on these quotients, which seem to be very mysterious objects of study. So that is where some kind of connection to combinatorial gadgets we have.
More questions? Okay, so if not, then yeah, let's thank Sunil. This was truly a very, very clear and very fascinating talk. And I think the only talk I've had where the speaker managed to bring together Galois, Lagrange, Euler, Fermat, and Gauss amidst other people. So this was wonderful. Thanks, Sunil.
Yeah, you're welcome. Yeah, so I'm glad you all enjoyed it. So thank you.
Sorry
And
to
you
put
can
you-
look up my papers. You can look up my papers for more details, and you can. I'm sure you can fish more interesting questions and projects from here. So thank you.
And sorry to put you so far past your bedtime. You can now go and sleep the sleep of the deserved.
Yeah, it's 1:30. So I got to the point now. It'll be hard to fall asleep now because my brain